Okay, everybody, welcome to class. Today we have just one or two small things left on chapter 4, polymers. And then we're going to move to chapter 5, which is all about defects. What I'm showing you here is the Toyota Mirai. I don't know if this is the one that just got released. Toyota Mirai has been around for a while. I don't remember how long. But they did just redesign it, and all of a sudden, it's a beautiful car. It's pretty good looking. So it's not a Prius. It sometimes gets put in the same category as a Prius. It used to look like a Prius, yeah. It was ugly. Yeah, and if you wanted to buy this one here today, this is an interesting vehicle in that if you tried to buy this today in Utah, it wouldn't do you a whole lot of good because unlike an electric vehicle or a plug-in electric vehicle or a hybrid, which either work on some combination of an internal combustion motor or a battery, right? Some combination of the two. This is a hydrogen vehicle, right? If you aren't familiar with the hydrogen energy, right, a solid oxide fuel cell, for example, or a polymer electrolyte fuel cell, essentially what it does, it takes oxygen and hydrogen as gases, it recombines them in the fuel cell, produces electricity and water vapor, which is pretty amazing, right? Because you could start out with water from the ocean, doesn't have to be fresh water. You could split that into hydrogen and oxygen. I'm saying that, and it's actually harder than it sounds. It's not as easy as you'd hope. But you can split them. We definitely have the technology to do this. It's not super cheap yet. And then you can recombine them, and there's no CO2 emission, right? This is a pretty amazing thing. And so right now you can buy these in Utah when you're good, but in California where there are hydrogen refueling stations, especially in urban centers, this is a pretty amazing car. And its cost isn't even like crazy. It's expensive, but it's not like more than a modern day, luxury vehicle. So what on earth does this have to do with what we're going to talk about today in terms of both polymers and defects? All right, that'll be to be determined, right? So we left off last time. We didn't quite finish polymers. The last thing we said is turns out there's a ton of different ways to make a polymer. Just because you have polystyrene, well, you have to think about the length of the chains. And then if you got a side group, are they all on the same side? Do they alternate? Is it totally random? If you have more than one monomer, right? If you have more than one monomer, how are they grouped? Do you have like a big block of the B monomer followed by a big block of the A monomer? Or do they alternate? Or are they random? Or do the B's branch off and the A is the main chain? All of these different options are possible, and it leads to a huge variety in the terms of properties that you can get, which is why polymers can do everything from be bulletproof like Kevlar, make strong ropes like nylon, to be, gels, basically. Totally, you can get wildly different properties. You can get, most of them are insulators, but we now know how to make them conducting, right? They can conduct electricity. You can do all sorts of stuff. You can make them so that they melt or that they just burn, right? That's the difference between thermoplastics and thermosets. A thermoplastic, when you heat it up, it will melt and it will flow. The reason for this is because the chains are only held together by weak secondary bonding, like a hydrogen bond or a van der Waals bond, right? Whereas a thermoset is something like the bakelite, where it's strong and covalently bonded in 3 dimensions, right? So it's not just one chain. The chains themselves are bonded to each other. So cross-linking makes a thermoplastic into a thermoset if you cross-link it enough. And a thermoset, when you heat it up, instead of flowing and melting like a thermoplastic, a thermoset will actually just burn, right? These bonds actually, you start breaking permanent bonds, covalent bonds, okay? One last thing that we should talk about is crystallinity. Polymers can actually crystallize, which is sort of a strange thing to think about, I think, for many students, because we've been describing it as a bowl of spaghetti, and that doesn't look very crystalline. But if it's some type of polymers, they actually can crystallize. You might get your polymer doing something like this, and if you got another polymer nearby it, maybe that's, let's draw one in the 3 dimensions. Oh, I'm going to really mess this up. That's really bad. Let me try and turn that into a unit cell, right? That could be your unit cell. This is awful. Do you guys kind of see that? Like you could get polymers that actually crystallize, right? What do you think is going to be a polymer that's going to be likely to crystallize? What attributes might it have that will make it likely to crystallize? Turn to your neighbor and tell him what attributes it might have. Okay, what do you think? Somebody give me an example of a polymer that might crystallize. Anybody? A polymer that will crystallize. What do you think? There's some on your homework this week. You can actually do diffraction on them. Most polymers, if I took just a random old polymer and I put it in the X-ray diffractometer, I won't see nice clean peaks typically. I'll see a really broad background, because instead of having regular repeating rows of atoms, like a crystal will give you, atoms are just everywhere. And so you don't see peaks from interplanar separation because there are no regular spacings. They're just random. But some polymers, they will. Anybody got a guess on what types will? Give me an example of a polymer that might crystallize. How about this? Alex, you got an idea?
Maybe just if they're like simpler polymers.
Yeah. Definitely the simpler the better. If you've got really long side groups, what's it going to do to this picture? Complicate it. Because that side group, which way is it rotating now, right? And that has to be arranged perfectly in a periodic lattice for it to be crystalline. So if you've got a side group that can rotate, that's not going to help you. Whereas if you have a double bond where that thing can't rotate, that's better. But a side group is still not preferred, right? You'd want it simple as possible. So things like polyethylene or Teflon, which is polyethylene but with fluorine groups, those can both crystallize. You can get close to 100% crystallinity on those, which is pretty amazing. They can be almost entirely crystalline. What else? Long or short chains? It's a tricky one. What do you think?
I think probably short chains, but just uniform chain lengths.
Yeah. I think what you'll see is that the portions that do crystallize, it's not like it's, crazy long. There's sections of it that repeat. So how do you have sections of a long polymer crystalline? We'll show you what that looks like in a moment. So these are the hallmarks of things that will be crystalline, but they can in fact crystallize, and in some polymers you can see diffraction really well, right? Danny was working on fake eyelashes for a while for a company that wanted us to characterize their eyelash material. What was it made of, PBT? It's a fairly crystalline material. You could see it in X-ray diffraction. You could see the peaks from PBT, these fake eyelashes, right? So how about this? Would you expect higher or lower density for a crystalline or amorphous polymer? I think this is our first clicker question today. I can't remember if it was like 60K or something. It's pretty awesome, though. So what, by the way, while you're doing this, what's the advantage of a hydrogen vehicle over just a Tesla or some other electric vehicle? Is there an advantage there? There's no emissions, except that maybe emissions went into splitting the water into hydrogen and oxygen. That might have taken emissions. If it was renewable, then it didn't. Are there other advantages, Isaac? That is the biggest advantage. If you have hydrogen vehicle, then all you have to do is fill it up with hydrogen and oxygen. Or better yet, use the oxygen and air and just fill it with hydrogen, right? That's what they do. The benefit is that you can do that in a couple of minutes. Filling up is no longer than filling up with gasoline. Yeah. It's expensive right now. Doesn't necessarily have to be. Yeah. 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 Right now they're expensive. Putting in the infrastructure is expensive. And then there's always this question that people usually bring up, like, okay, what if you're in an accident? Is it going to be like the Hindenburg, this giant hydrogen blimp that went huge explosion? We had a guy come and give a talk 2 years ago who worked on hydrogen storage for vehicles. And they actually tried to make these things explode. That was his job. He tried to design a tank that would be least likely to explode. And it's far harder than you think to make these things explode. It becomes a flamethrower, but it doesn't explode. Right? If you puncture it and it does ignite, it'll just spray flame until it exhausts the hydrogen. But it's tough to make them explode. But that was his counter argument. He's like, cars explode all the time. Anyways. All right, I'm going to wrap this up. All right, what do people think? Which one's higher density? Hopefully, yeah. So the majority of people think crystalline. Somebody explain to me why it's going to be higher density. Yeah. Yeah, if you take a climbing rope and you actually do a butterfly or somehow coil it, it's going to take up less space than if you just throw it in a bag, for sure. Yeah, Jaden? There's a lot of empty spots, yeah. You will lose Tetris. That's a good one. Other ones? Yeah, Eric?
So I answered the wrong question, but
Okay.
the wrong answer, but I'd like to justify that a little.
Oh, let's hear it. Counter argument.
So amorphous ice, right? So the reason why ice expands when water freezes
Oh,
is
yeah.
because you have the hydrogen bonds, which
It's a great point.
the volume. And since in ice, in structured ice, you have 4 hydrogen bonds per water molecule. In liquid ice, you
Yep.
don't have that.
The same exact thing happens with a number of materials. Like carbon or silicon. Melting carbon's stupid hard. So let's pick something that we can melt pretty easily, like silicon. Silicon has the same structure as carbon. It's this one right here. It looks like zinc blende. It's not because it's all the same atom. Otherwise, it's zinc blende. So look at this one. Silicon, just like carbon, wants to have 4 bonds. So you end up with this structure that has lots of empty space in it. And so when you melt this thing, you no longer are bonded. By definition, when you melt it, you're breaking those bonds. And so it actually shrinks. So some materials actually increase volume when they solidify. It's the exception to the rule, not the rule, though. So because polymers in general are much more dense in the crystalline state, we can use density as a way to measure crystallinity. The two are related, right? So here's how it works. The percent crystallinity, if you're trying to calculate that, the percent crystallinity will be equal to the density of the sample in its completely crystalline form. How do you get that? You get that from X-ray diffraction. You do X-ray diffraction and you measure the unit cell. You know how many repeat units are inside of it, hopefully. You can figure out what the theoretical density is. That's your crystalline density, right? You measure the density of your sample, rho S, and then you need to know what the density of a completely amorphous sample is. So maybe one that started out as a liquid and you cooled it really quickly so it didn't have a chance to crystallize. If you know those 3 densities, then you can use this formula to calculate what's the percent crystallinity, which is pretty slick because otherwise it's challenging to tell how crystalline a polymer is, right? This paper is a polymer, so how crystalline is it? What would you do to do this? Like, that's hard. You could do X-ray, and what you'll probably see, even if it's a material that does have peaks, more than likely you'll see this. The intensity versus 2 theta will have some amorphous background like that, and it'll have peaks on top of it. So how do you know how much of it is crystalline and how much of it is amorphous? You know that both are present because you see both peaks and the amorphous bump. So how do you determine it? Turns out density is a pretty slick tool. There's other things you can do, but this is a pretty easy one because you can measure density very easily. Okay? Yeah, question? What was what now? Oh, rho of A would be the density of the completely amorphous version of that polymer. And how do you get a completely amorphous version? Typically, you melt it and then you quench it really quickly. So by quenching it quickly, you don't give it time for these polymer strands to line up in the nice arrangement that we see up there. So instead, you measure the density of that, and hopefully that represents your amorphous one. Realistically, when Danny did this for a recent project, we just looked it up. The literature values are oftentimes reported for many of the polymers you probably care about. Jaden?
Just to clarify, amorphous is when it doesn't make a crystal
Yeah.
structure?
Amorphous, A means without, morph means structure, so without a structure is glassy or amorphous. Right, non-crystalline. Okay. Yeah, DSC will also tell you, right? And we won't get into it in this class because I don't have time, but there's other ways of measuring crystallinity that are pretty good, like scanning calorimetry is a pretty good way. Thank you for reminding me. So how do things actually crystallize? It's not like the whole polymer strand just straightens out and lines up with another one next to it because entropy is still there. And so you find a middle ground. Here's what you typically have. You've got regions of the polymer that fold up on itself in a crystalline manner, right? These things sort of fold up and you get this chunk that's crystalline, and you might have, we would call this a grain boundary if this was not a polymer. It looks like a region between crystalline sections, so it's kind of like a grain boundary for polymers. So these are called micelles or spherulites. They typically grow radially outwards. They're sort of spherical. And so globs of polymer, if you were to zoom in close enough and look at them, this is one of the common pictures that you'll see to represent polymers, where there's both amorphous regions and then crystalline lamellar regions also forming in there. Okay? Any questions about this? Yeah, Jaden?
So, in a sample, does it create multiple blobs like you were
Yeah.
saying?
Yeah.
Okay, does that, like, I know that would increase the density, but does that make it, like, more brittle, or, like, having blobs that are less?
Yeah, okay, so you've got a big vat of material. You start to cool it down. Things typically start to crystallize on the edges for reasons that we'll learn about in 5 chapters, right? So over here it starts to form a little sphere, and over here it does, and those spheres are going to sort of grow together. Maybe your question is, does that influence your mechanical properties? And yeah, it does. Yeah, the size of these spherulites, in the same way that grain size influences hardness and yield strength in crystalline and ceramic materials, yeah, same exact sort of things can happen. Okay, let's shift gears and talk about defects now. So we've talked about perfect lattices, and now we're going to shift gears and talk about what happens when things aren't perfect, and why does that give us things like the Toyota Mirai, right? Or Mirai car, right? So our objectives for today are we're going to talk about point defects. These are defects that occur in one point. They're not a line, they're not a plane, they're not a three-dimensional object. It's a single point in your crystal that's wrong. Something's wrong there, okay? We're going to calculate total thermal expansion, and we're going to do that in terms of vacancies as well as just the lattice parameter expanding. Both of those things will lead to your total thermal expansion. We'll maybe get some time to talk about important alloys at the end. Okay, so I'm going to skip some of this and just dive right into point defects so we have time. So point defects can exist in a variety of different ways. The two most common ones that we're going to talk about are going to be either vacancies, interstitials, or substitutions, right? I guess those are kind of three, right? You can either have a vacancy, which would be if this was all a bunch of atoms, and I pluck a student out, I created a vacant seat, right? I can see next to this guy there's a vacancy. There's vacancies kind of all over, right? So this would be symbolic of like a real material. Like vacancies exist in real materials. You can't get rid of them very easily because there's a reason that they want to exist. We'll get to that. Now the other option is you can have either a substitution, like let's say instead of a student, I put a dog in a seat. So I pull a student out and I put a dog there, right? It's a different type of occupant of that seat. We can do the same thing. You can pull out a silver and you can put a gold or a copper, right? That's how you make sterling silver. You replace some of the silver with copper, right? Sterling silver is now a new alloy that forms. Or you can form interstitials. An interstitial is, let's say I took a dog and I put it between these two students on the floor, kind of in the space between them. There is technically a spot right here. It's not very big. It would be hard to put a desk there with a student in it, but something like a dog I could put there, right? So that's an interstitial, okay? If it's a self-interstitial, then you're talking about the atom that is there is the same one that would normally be in a seat. It's just not in its seat. Like if Amelia stood up and encroached on one of her neighbors, she would become a self-interstitial, and she would create a vacancy in that process, right? Everybody with me? And those are all point defects. They occur at one spot in the crystal. They don't propagate through, right? They occur at one spot, so we call them point defects or zero-dimensional defects, okay? So the question is, what are our driving forces for forming and preventing these? This is our next clicker questions. Whenever I ask why something happens, it's either entropy or enthalpy. Yeah, question?
With the interstitials, is it the same kind of atom, just oriented differently, or is it a different?
Same type of atom. It's just, let's say that there's these 6 students here. I could either put a 7th student in there, that would be an interstitial, or we could have a student get up out of a seat and stand in the middle. That's still an interstitial. Those are all self-interstitials. Okay, the question I have for you is this. What drives vacancy formation, A, B, C, or D? I know you're tempted to put C or D, but don't do it. Resist the temptation. It's either A or B. Okay, I'm going to close the poll. Get your answers in. My network seems to be slow. Too many people using the Wi-Fi. Okay, answers, it looks like they're in now. Okay, what's driving formation? Yeah, entropy. So explain to me why on earth entropy wants somebody. Who was it? All right. Why on earth does entropy want vacancies to form? Because it's more disordered, right? This first 2 rows of students is completely filled. So there's only one way of organizing it, and that's every student gets a seat, right? Now consider the first 3 rows where I've got some empty seats. Consider all the different possibilities of where I could put these 1, 2, 3 empty seats. I could arrange them in all sorts of ways. I increase the disorder of my system because I can move that disorder, that vacant seat all over the place. So from an entropy standpoint, it would love it if every lattice was half filled. At half empty and half full, that's where you maximize entropy. There's no way to increase the amount of configurations beyond half full. Yeah, Jaden?
So this is going back to something you said a little bit earlier, but you said a vacancy or a self-interstitial doesn't propagate, like it doesn't affect, it doesn't move everything else around it.
Uh-huh.
So why is that? Is that just because the rest of the bonds are strong enough to keep it from shifting?
Well, because they can exist at a single point. Like, just like you could stand up and crowd your neighbor, and Danny would have no idea that you did that, there's no reason why it has to propagate through the material. Now, in practice, you will create a strain field. If you stand up and crowd your neighbor, you make him uncomfortable, and the other people around him uncomfortable. The atoms get the same thing. They get that same sort of discomfort because you're squishing their bonds or stretching their bonds. And so it will have a local sphere of influence, but it's occurring at a point in the lattice, not a line or a plane.
So why doesn't me getting incredibly close to my neighbor not force them to shift a little bit, to move, to like, because like if I got really close to him, he might get
Yeah,
strong,
so
but it does
I'd say hold that thought for later, actually tomorrow. So actually, let me make a comment about tomorrow. So Friday, I have to travel. One of the perks of you guys going to a Research One Institute is that your faculty are both researchers and teachers. The downside is that we have to travel sometimes. So I have to go to Qatar of all places. I'll be gone Friday, Monday, and Wednesday. So I've already pre-recorded the lectures. I'll put those on YouTube. And in class, if you come, they're not just going to hit play on the YouTube. They'll do example problems. So you don't have to come to class. If you want to come to class, the TAs will do example problems. And when you watch the next video, we'll talk about how defects can influence one another and answer your question. Homework will still be due Wednesday. The TAs are still around. I'm just on another continent. All right, how about this one? So I've just said the following. I said that from an entropy standpoint, 50% of the sites would be occupied and 50% would be vacant. And that's not what we get in crystals. It's more like 1 in 1,000 or something like that are empty. So why? What's preventing it? A, B, C, or D? This one says multiple answers are acceptable. So there's not just one right answer here. Okay, so get your answers in. Okay, I'm going to close the poll. Get your answers in. Meanwhile, what do you guys think? Somebody want to explain their reasoning on one of these, why you answered the way you did? Anybody? 30 people still need to answer, which is concerning. Yeah.
From moving in the first place.
Yep. So strain is definitely an acceptable answer. What are the other ones? Enthalpy is broken bonds. That's going to make sense. Jaden?
I was just going to say, in the last case, the correct answer was entropy, and if this is the exact opposite, then I would think it would be the exact opposite reason being enthalpy.
Yeah. I need to add this one as the correct answer. I'll fix that after class. But yeah, it's the opposite of entropy. So you know it's got to be one of the other three. And then broken bonds and enthalpy is essentially saying the same things. Bonding is related to enthalpy. So I'll fix that submission. That one's broken. All right. So vacancies are what we call thermally activated. We've seen this equation before. Whenever you see in material science the equation where some property is equal to some coefficient multiplied by an exponential with an activation energy divided by a thermal energy, we call this an Arrhenius equation, named after Arrhenius, the Swedish guy who discovered this, right? So what this says is NV, that's the number of, at equilibrium, of vacancy sites. Okay? N is your total number of atom sites, right? So in this room, we could count the number of seats in this middle section. We could count how many vacancies there are, and NV divided by N would be that fraction, right? The number of vacancies divided by the total number of seats. That would be the fraction. So oftentimes you'll see this N brought over to this side of the equation, NV divided by N, and it's the fraction of empty seats, of empty lattice sites. Then you've got your vacancy formation energy, the formation energy for creating a single vacancy, and then thermal temperature. So the warmer and the warmer your material is, the more vacancies you get, right? This is because enthalpy and entropy, in this case, don't have the same temperature dependence. And entropy starts to win. When you heat it up, entropy is more dominant and it wants to create more vacancies. But we're never talking about a huge, crazy number, right? We could plug these things in and see how many we have. Let's do it for copper. Where the activation energy is 1 electron volt, I want you to plug in what will be the vacancy concentration, which is just NV divided by N. That is the concentration at 800 Kelvin. Okay, quick on this one. We don't spend a lot of time. It's a simple calculation. The answer, you're going to, is it 5e to the negative 4th, 5e to the negative 5, 5e to the negative 6, or 5e to the negative 7? The most common mistake I see on questions like this is using the wrong Boltzmann constant with the wrong units. You have to make sure, since we have electron volts, you need to use the unit that has electron volts, or doing the temperature in Celsius instead of Kelvin. Definitely the most common two mistakes, or forgetting the negative sign. So punch that in. We should get, this shouldn't take super long. Okay, I'm going to close the poll here in a minute, get those answers in. Okay, going to wrap it up. Okay. People think 5e to the negative 7. Okay. So that's right. 5e to the negative 7, what does that mean? Can you put that into context? Well, 5e to the negative 7, that means that there are 5 vacancies for every 10 million sites. That's crazy, right? That's really a small number. So we're not talking about a humongous number of vacancies. 5 per 10 million is not very many, right? Now, the amount that you're going to find will depend on temperature. If we went to a higher temperature, we'd see that number go up. Or if the activation energy was smaller, we'd see that go up as well. Yeah, Jaden and then Sam. You could solve for it, so we do the following. First off, we found that it was 5e to the negative 7. So you could set that equal to x out of 10 million, and you'd find that x is equal to 5. If you pick some other number, you get not number 5, you get 50 or 0.5 or something like that. Okay? Any questions on this so far? Okay. So most metals have NV over N. At their melting temperature, the point at which they're melting, you're still only at 1e to the negative 4, so 1 per, is that 1,000 or 10,000? It's not very common. Oh, 1 per 10,000, right? So it's still not like it's a super prevalent thing. Your material is not riddled with vacancies for the most part, okay? Now, we've said the following. We've said that all sorts of different point defects can exist. You can have this. Atom 5 here at position 5 is too big compared to the lattice around it. So it's going to squeeze the lattice around it. It's going to put the lattice in compression, right? It's crowding them. Meanwhile, you've got atom 4 is too small, so it's going to put the lattice under tension. You've got atom 2 is a self-interstitial. There's no seat there, but it created its own seat, right? Atom 3 is a non-self-interstitial. It's just what we call an interstitial. It's some other atom occupying an empty spot. And then you can have over here the vacancy. All of these different things are possible as point defects, okay? And they have different formation energies, right? The activation energy for all 5 of these different things, no way would it be equal. The one that costs the least energy will have the smallest activation energy, probably the vacancy. The vacancy followed by the interstitial or this one, and then finally these two are probably your most expensive because crowding atoms is always there's a bigger energy penalty, right? Okay, so, no, we're going to skip that one. All right, how does this change in ceramics? In ceramics, the big difference between ceramics was we had 2 different ions at least, which had both a difference in size and a difference in charge. So we have to take that into account with our point defects that can form. If you have sodium chloride, rock salt, and I pull out a sodium ion, it's now no longer charge balanced, right? I removed the positive charge, and that's a really bad thing to have happen in these things. It really wants to preserve electroneutrality. So because of that, it's very common that you get defects occurring in pairs in ceramics. It's very rare that you have a single defect because that would influence your electroneutrality. So instead they come in pairs. So here's 2 common ones named after a Soviet and a German in the 20s. You've got Yakov Frenkel's defect, and this is when you have a cation vacancy and a cation interstitial. So what does this look like? It would look like which one of these pictures is showing the Frenkel defect? A cation vacancy and a cation interstitial. So let's take the sodium as our cation, right? Normally this would be filled with a sodium site, but that sodium atom left its seat and it came to crowd these ones over here. These 2 together represent a Frenkel defect. It's a pair. It's a pair of defects. This one over here is the same thing. This is a Frenkel defect, these pair. This sodium left its seat and it's now over here. Okay? That's your Frenkel defect. And then you've got schottky. A schottky defect is like a missing sodium and a missing chlorine. Overall, both of these preserve electroneutrality. How are you going to remember them? I don't know. I like to remember Frenkel because Frank's kind of a creepy name. Sorry, Franks. And Frank's crowding your personal space. So there's your Frenkel defect. Okay? Any questions on Frenkel versus schottky defects or defects in ceramics in general right now? Yeah, Isaac?
So I assume that the Frenkel is specifically cations and significantly smaller?
Great question. Yeah, so he's got a really good line of reasoning. Let's go through. He said, is a Frenkel much more likely to be a cation than an anion? Yeah, because it's smaller. Because think, this guy had to leave, and now you've got a small cation which can fit in these interstitial spots. The anion, like chlorine or oxygen, is ginormous. So even if you create a vacancy, we're going to put a ginormous atom over here. So it's much more likely to be cation. That's a great observation. That's absolutely true. Other questions about this? Let's keep going. Okay, how about this? If I take an atom from the center of a material and I move it to the surface, should there be a difference in energy? Why or why not? Or in other words, if I take Caleb out of the middle of this section here, I pluck him up, I create a vacancy there, but I slide a seat right here on the front and I put a Caleb here, is there a difference in energy? Or have I just like shuffled things around? What do you think? Why is there a difference? I've changed the surface energy, right? This is now flat plus a bump, so it has a surface energy. Why do surfaces cost energy in the first place? They don't have the number of bonds they want to have. Caleb's already only got 3 bonds over there. He's got the missing person behind him. If I put him up here, he's only bonded to Alan. And that's not a state he wants to be in. He's missing all sorts of people next to him, right? Atoms are the exact same way. You can count their bonds and figure out what's the biggest energy penalty. So for example, placing an atom right here in the middle of a surface is the least desirable because it only bonds the thing below it. Now if I place one right here, it bonds below it and this edge, right? If I put it at the kink in an edge, then it's bonded to 3. If I put it in this spot, it's going to be bonded to 1, 2, 3, 4. So there's preference, right? And because of this, you start to see when atoms grow, they get picky about where they grow. So if you've got new atoms coming in from like the vapor phase, right? If you're sputtering this, for example, or if you're pulling them from the interior via vacancy formation, they don't just randomly go wherever on the surface. They go where they lower their energy, and that's going to be where they can form the most bonds. So along edges, along those kink spots, that's going to be the best spots for them to form. Any questions about this? Yeah.
So just to clarify, what would be the actual answer to the problem?
So there is a difference in energy. Because think, Caleb right now has 3 bonds. We're going to break 3 bonds, and we're going to move him right here where he forms 1 bond, and there's some difference in entropy. Overall, yeah, there's probably going to be a difference in energy. Yeah, it's a change in energy. Probably it's going to go up in energy. It's not going to want to do that likely. Unless the entropy benefit is large enough by creating that vacancy, and there's a balance to be had there. And we're not going to actually learn to explicitly calculate those, but in quantum mechanics or physical chemistry, you do learn how to do that. Jaden?
So when there are basically like the desirable locations to bond are taken up, then it just flipping a coin where it could go.
Yeah, that's exactly right. So if you go back to the ledge situation, if, for example, we said that these spots are the best right here, like this one and that one, if those are filled, if those aren't available, then it could go either here, 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 or here at all the same energy cost. So it's sort of a coin flip. Maybe it's the one that it's closest to, or yeah. There's no energy reason why one's better than the other. I'm going to skip this derivation. It's basically just describing how on earth did we end up with this expression, this Arrhenius expression. And because we're a little short on time, you can read it if you want. It's not going to be something I test you on. Okay, non-stoichiometric defects are also possible. And iron oxide's a great one. This is named after Fritz Wust. He's a German guy, the founder of the Max Planck Institutes. That's like the German national labs. That's this guy. He's an important person. They named a mineral after him. It's iron oxide. And it's not just any iron oxide, because iron can take multiple different cation oxidation states. This is FeO when it's +2, right? So you've got +2 and -2, so it's a 1-to-1 compound. But we know that iron can also be +2, +3. It can be all sorts of goofy things, right? So imagine for a minute if you had a mixture of Fe2+ and 3+. So now you've got more than a +2 charge here. Maybe you've got an average of 2.5, right? Well, what are you going to do to balance that out? You could either try and add more negative to this. That means that you're going to cram oxygen in the structure. What do we know about that and its likelihood? Is that a good idea or a bad idea? It's a super bad idea. Oxygen is going to crowd it too much, so it's unlikely that you're going to cram extra oxygen in here. So what do? We can form additional vacancies, right? So here's how it works. For every, so let's see about this right here. So it says for every 1 Fe2+ vacancy, if we just remove one of these iron 2+, we could have 2 compensating Fe3+ cations and have it still be charge neutral. Okay? So you can dope materials. You can intentionally change their stoichiometric ratio to create vacancies. With wustite, it has lots of vacancies that it can tolerate. Way more than the 1 in 10,000 that most metals have at their melting point. You can generate huge fractions, 1 in 10, 1 in 5. You can generate really, really high fractions of vacancies. This is what's getting us closer to the Toyota Mirai, right? We're not quite there. Let's first relate this to thermal expansion. Okay, if you've got materials and you heat them up, they're going to expand. The amount that they're going to expand, right, so this will be our percent change in length. We know that the vast majority of materials, they look like this when you heat them up. It might be linear, right? That's your overall delta L over L. Delta L over L is right there, okay? And up till now in this class, we've said that the reason this happens is what? Somebody remind me, why do things expand? we have our potential energy well, and it's not symmetric, it's asymmetric, so the average position's getting further apart, right? So it's lattice expansion. Literally, when you heat this up, the atoms spread out a little bit, most materials. So there's actually something else to it. We have been skipping this up until now because we didn't know what vacancies were, but there's actually this happening. This is delta A over A. So that's your lattice parameter expansion, right? And it's dominating. It's by far the most important thing here that leads to thermal expansion. But there is a non-negligible, like you can't ignore it, amount of thermal expansion at any given temperature, which is due to NV divided by N all over 3. It's vacancies, right? If I heat this material up, let's assume it was completely occupied by students. As I start to heat it up, I start to form vacancies. So I pluck Caleb out because he wants to form a vacancy, and he comes and he sits on the surface. Well, he just made the material a little bit bigger by doing that. And as I heat it up more and more Calebs start to come and sit on the surface up here until our material is actually expanding just due to vacancies moving and migrating to, atoms migrating to the surface and creating vacancies in their stead. This makes sense? So it's a small fraction, but it's a non-negligible amount. And what's cool is that you can actually measure this. You can determine how many there are, okay? So the expression would be right here, that the fraction of vacancies is going to be equal to NV over N. That's equal to 3 times your observed linear change in your of your material. It's going to expand. So this is your observed thermal expansion, and this is the expansion of the lattice. How on earth do you measure the expansion of the lattice? How would you do that? Using tools that we've learned in this class. You do XRD, our old friend XRD. We love XRD. It tells us the lattice parameter. All you have to do is have an X-ray diffractometer where you can heat it up, right? How do they do that? There's lots of ways. The most simple way is they take a strip of metal, you put your sample on top of it, you're hitting it with X-rays, and they're doing their thing, and you just pass a current right through this metal, and it heats up. You put a thermoprobe on the backside so you know the temperature, and using that, you can solve X-ray diffraction at a bunch of different temperatures. You guys did this on the last homework or something, the Vesta one, and you figured out what delta A over A was. So if you know that, you measure that, you can figure out your vacancy concentration. You can use that to figure out formation energies and all these things that we might care about with vacancies. Jaden and then Alex.
Sorry if you're getting annoyed with my endless questions, but you said that Caleb would go to the edge of the.
The Caleb would go to the edge of the material.
So, do they actually completely relocate all the way from wherever they're at to the very surface?
Great question. Does that atom move all the way to the surface? What do you guys think? How easy would it be for Caleb to climb over people all the way to get to here? Not so easy. That's a long way for one thing maybe, and he's going to upset a lot of people in the process. Instead, what if he got up and he moved to the seat in front of him, right? And then the person behind him could go to that seat. Or rather, what if a vacancy starts out here, like she moves to the surface, now there's an empty seat, and then Tyler, I'm close. Tyler takes that seat, that creates a vacancy there. So the vacancy travels that way and the atoms travel this way. That makes sense? So it's like a hopping mechanism, really is what it is. So it's not like that atom makes it to the surface. That atom moves a little bit forward, and everything else gets shifted with it. Yeah?
So what causes the person behind Caleb not to move forward? What causes the vacancies?
So why do things move at all has to do with diffusion, and we'll get there in 3 chapters. So hold that thought. Yeah? That's the fraction of vacancies. It's the fraction of empty seats. Alex, do you have another question? Yep. So at any given temperature, we could calculate this distance between these two, and we could use that to calculate a formation energy. And in years past, I did a homework question on that. I think I removed it this year. So it's just free knowledge. Totally free. You're getting your tuition money worth. All right, we're almost done with today. I want to talk a little bit about alloys. We've been talking about pure materials for the most part, but you can dope them, right? We've already said that sterling silver, right, is when you mix silver and copper. You do that because it makes it stronger for reasons that we will learn very soon, right? You can take stainless steel where you add 12% of chromium by weight instead of iron, and that makes it form this corrosion impervious layer, which prevents it from oxidizing, right? A lot of these things, we do them by design. Muntz metal, right? They made boats out of this stuff because it's super corrosion resistant even to salt water. So solder. We use solder, which is a mixture of lead and tin because it melts at a low temperature. So you don't have to have a really hot soldering iron. You can use a low temperature soldering iron. There's lots of different things why you might want alloys. Sometimes you want it to be totally pure. If you're working in the semiconductor industry, like you're designing the next new iPhone or whatever, when they make silicon, they get it crazy, crazy pure. Often they'll call it 99, so it's 99 point, you count these up, there's 9 of these 9s. It's that pure, right? So there's like 1 impurity per billion atoms or something. It's rare that you need that, though. Oftentimes we make do with much less pure materials, right? And getting it pure is challenging. Like, think what you know about entropy. Entropy wants to mix things. So when you go the other way, it's going to cost energy, and it's just hard. You have to think of a mechanism. How would you actually separate these? And there's whole industries trying to separate to purify silicon. Okay? So the last thing I want to say is, we'll skip that for now, and let's talk about aliovalent substitution. This is finally where we get to Toyota Mirai and cars like it. They work by having fuel cells. A fuel cell works like this. You've got, let's say, oxygen out here, and in this case, you have a lack of oxygen. So this is not a fuel cell, this is a fuel sensor, an oxygen sensor, but it's the same material, just operated in reverse. In this case, your vehicle generates gas, the emissions from your gasoline engine is mostly not oxygen. If you're doing it right, you're burning all your oxygen, so you'd have none here, right? I might have this backwards. In any case, you've got oxygen on one side, no oxygen on the other. You've got air, which is 21% oxygen on one side, and you've got fuel combustion, which is mostly no oxygen. What they do is they take yttria stabilized zirconia. We've talked about that before. That's our friend ceramic steel, right? The stuff that you make like the ceramic knife out of, the same stuff. You started out with YSZ. So you start out with zirconia, ZrO2. Zirconia is 4+. We're going to put an yttrium on there, which is 3+. What's going to happen when I put a 3+ on a 4+ site? It's no longer charge neutral. That won't stand, right? We don't allow that in ceramics. So what do? You don't have enough positive charge, so we have two options. We can either add positive charge by cramming in extra cations in there somewhere, not likely, or if we have not enough positive charge, we can remove some of the negative to make it neutral. That make sense? So what do we have to remove negative? We have oxygen. Oxygen comes in units of 2-. Each oxygen you take out, you remove 2 electron negative charges, right? So for every 2 yttriums that you substitute, for every 2 of these, you get 1 oxygen vacancy. This makes sense? For every 2 substitutions of an yttrium 3+ on a zirconium 4+ site, you create an oxygen vacancy. By filling this thing with lots and lots of oxygen vacancies, you have a pathway for oxygen to travel through this sensor. It wouldn't be possible if you didn't have these vacant seats. In the same way that if I wanted to, I could put a bunch of vacant seats in here, and then I could awkwardly kind of climb over people, and I could move through this material. It's not like it's super easy. It's not like it's great conduction, but at least there is some conduction there. It's exactly what's happening here. Now, for it to happen, an oxygen molecule is O2. That has to split. You have to get an oxygen ion, so you have to give it electrons. It becomes oxygen 2-, and now it can travel through. Oxygen gas cannot travel through, or this device wouldn't work. So this is amazing. Think what it does. On one side, it's picking up electrons, right? So you've got electrical current going this way. You've got O2 gas here. It travels through, and it becomes O2 gas again by surrendering electrons. So you have a circuit. You have an electrical circuit. It picks up electrons. Now it travels as an ion. It surrenders those electrons. And so you can measure a circuit here. You can measure a voltage. And this is what happens in your vehicle. When you have a electronic fuel injection, EFI, if you ever noticed your vehicle says like EFI live or something, it's electronic fuel injection live, meaning in real time, as your motor changes the air to fuel ratio, you're going to change the amount of oxygen in your exhaust. And what you'd like to do is tune that just to the right amount where there's no oxygen. And how they do that is they measure a voltage from this electrical current. They measure what the voltage is here. That tells you what the partial pressure of oxygen is here. So in real time, you can adjust it to get peak performance and avoid fouling and soot and pollutants that aren't necessary, which is pretty rad. Now that's if you're measuring it. In this case, you're providing a small difference, right? This is just a small amount of gas. And from air, you can measure a voltage. If you give it lots and lots of no oxygen, right, hydrogen, and lots of pure oxygen on the other side, then you can combine these and you can harness this electrical voltage, and that's how the Toyota Mirai is able to produce electricity to power its electric motors with just hydrogen and oxygen. Now, this vehicle doesn't use YSZ. It uses a polymer version of, it's almost the same thing, it's just different materials, and we'll get to that probably next class. Okay.